The second chapter of the course is about the Zariski topology. So looking back, what we have done in the first chapter is we defined affine varieties in the affine space AN, and we defined them as subsets of this space. And also towards the end, we defined what we mean by polynomial functions from such an affine variety into the base field K. The next thing is that we slowly start adding more structure to this set. And I mean, you have seen this in various other lectures. So for example, in analysis, you start by defining the real numbers first as a set, how you can describe them. Then you maybe give them some metric, or at least to define what it means for sequences to converge. Then you talk about how can you add them, so you make them into an abelian group. Then you talk about can also multiply them, so you make them into a field, and so on. So gradually you add more and more structure to this thing. And this is what we're going to do with affine varieties. And in this chapter now, the extra structure that we place on affine varieties is that we give them a topology. So we make them into topological spaces, and this determines many of the properties of this affine variety, which are studied later. So for example, the decomposition into different components, and also, surprisingly, some notion of dimension, which we can extract from this topology. And so the entire chapter will be about these topological notions. And I know this is a mandatory course at ETH, but if you need a refresher, I'm going to put up a short video kind of as an appendix where I remind you about these basics of topology. One thing compared to the standard treatment of topology, which is peculiar about these notions in algebraic geometry, is that it will be nice to define a topology not in terms of its system of open sets, but in fact by specifying what the system of closed sets is, because these are more natural in the algebraic geometry side. And so this appendix video actually explains all these topological notions in terms of the closed sets. Now, because a set system is, a set is closed if and only if its complement is open, you can see that the open sets and the closed sets determine each other. And so in principle, all the theory can just be formulated in terms of what the closed sets should satisfy. And so it might be good brain gymnastics for you to think about it for yourself and then maybe check with this appendix video to make sure you got everything. Okay, so let's assume we are all on board with basic topology, and then defining the Zariski topology is actually not so hard. So if you are given an affine variety X, then the Zariski topology on X is just the unique topology whose closed sets are exactly the affine subvarieties Y in X. And recall, this just means these are defined by taking any subset S of the coordinate ring of X and then looking at this relative vanishing set like this. And a basic kind of sanity check that you should do for yourself is that this is indeed a topology. So there's kind of three axioms that the topology needs to satisfy. That empty set and the entire set are in there, that finite unions of closed sets are again closed, and that infinite intersections of closed, or possibly infinite intersections of closed sets are again closed. And this corresponds exactly to things which we have already seen before. And to just give a small example, when X is A1, the affine line, then the Zariski topology is exactly the finite topology, which translated just means that a subset of A1 is closed if and only if it's either finite or it is all of A1. And this thing is called cofinite topology because the complements of the open sets are either everything or finite sets. And since we formulate things here with the closed sets, this actually becomes more natural by just saying closed sets are either finite or everything. Okay. And so, I mean, this is the definition of the Zariski topology, and the next exercise should convince you that this topology is a bit weird compared to many of the topologies that you have seen before. So, for example, on closed subsets of some Euclidean space or some C to the n. So it should make you a bit wary of this topology. So it means you can't always trust your intuitions in this area. You should really go down to the basic definitions and check things for yourself there. So what I mean here is that even on this simple space A1, the topology has some strange properties. So for example, if you have any non-repeating sequence A1, A2, A3, and so on, which means that no, so this is a sequence in A1, and non-repeating means there's no n comma m with n not equal to m, such that an is equal to am. If you have such a sequence, then the claim is that this sequence converges to any point in A1. So in particular, the limits are not unique in A1. Second is that any injective map from A1 to A1 is continuous in the Zariski topology. And then a kind of more open-ended exercise, like pick your list of your favorite properties of topological spaces, which you still remember. So for example, space can be Hausdorff or compact or connected and so on. And check whether this A1 with this Zariski topology has them. That's a kind of instructive thing to go through. And finally, there's also something weird because, I mean, recall there is something called the product topology. So if you have two topological spaces, you take their product, then there is a natural topology on that product induced from the two factors. And certainly it is true, and we have seen that A2 is the product of A1 with A1 as sets. However, now this means that there's two topologies on A2. One is the product topology induced from this here. The second is the Zariski topology on A2 as it is defined before, because A2 is also an affine variety. And you can show, however, that these are not the same. So somehow it's not compatible really with this product topology construction. And the hint for that part is you can consider the diagonal inside A2, where the set of points where the two components are the same. And you can show that this is closed in the Zariski topology, but it's not closed in the product topology. And this last, I mean, if you actually check this, you will need something about the base field K, which is a consequence of K being an algebraically closed field. So just as a kind of hint, if you try this exercise. So it sounds a bit weird that I started by defining this Zariski topology and then telling you all that is bad about it. But I guess this is just being a bit honest up front. But let me maybe skip to the summary here. So the Zariski topology is weird. That has been demonstrated by the exercise, but it has two great features. Namely, first of all, it is defined over every algebraically closed field K. In a certain sense, if we want to develop some theory like algebraic geometry, which reflects like as large a part of commutative algebra as possible, then really, I mean, when we want to define a topology, for example, we can only work with what we have, namely with functions, their maps to the base field, and so on. And the Zariski topology is only using these notions from commutative algebra. And so indeed, it can be defined independent of the base field. And as we're going to see in the next sections, it is good enough for a lot of purposes. And in fact, in certain, in a lot of ways, these kind of bugs that we saw above turn out to be features which allow us to, for example, to define the dimension of X purely in terms of its topology. A final note that I wanted to add here is that the Zariski topology on X, this was what we defined. Well, if X is contained in AN, then you can check this Zariski topology on X is also the relative topology of the Zariski topology of AN. So that's a general thing, that if you have one set contained in another, and the bigger set has a topology, then you always get for free a topology on this subset. And this works out here. So at least this compatibility is satisfied by the Zariski topologies. And this just uses, well, a closed set of X is a subvariety of X. But then we have seen one of the properties of subvarieties of X are exactly the affine varieties in the bigger space AN, which happen to be contained in X. But then you see the affine varieties in AN, these are the closed sets here. And so this means any closed set here is the intersection of a closed set here with X. And this shows you kind of one direction, and then you can also check the other direction. Okay, this was just a basic definition and gaining some intuition about it. And then in the next sections, we're going to see how can we put this topology to use to formalize some properties and some interesting notions on affine varieties X.